Hi, Matthew from BMI Academy. Welcome to our chemistry class. And our focus today would be on JUPEB Chemistry Practical Revision 2026. As usual, for JUPEB Chemistry, we have two questions. One from quantitative analysis, which you can also call the volumetric analysis, though volumetric analysis is a portion under quantitative analysis. And the very area we test under this is titration. While the second question is usually qualitative analysis, which is basically salt analysis, dealing with identifying cations and anions. But our focus today will be on titrations. This year's JUPEB involved a redox titration, a titration involving a transfer of electrons. And the two solutions involved are solution A and solution B. Solution A is a 3.92 gram of ammonium iron 2 sulfate, while solution B is potassium permanganate, KMnO4. This particular question here is a model, like basically a simulation, where we tend to give a known concentration to solution A and having solution B with an unknown concentration. Or we say solution A is a standard solution, while solution B is not. And the aim of the experiment is to determine the concentration of B. And mind you, the exam can be remodeled in such a way that the concentration of B might be supplied. The aim can then be channeled to maybe identifying an unknown element labeled as probably X. Before I proceed, I need you to note the following. I did this so as not to make this video unnecessarily long. Number one, this is a redox titration, like I've said before, and any redox titration involves reduction and oxidation, and which is basically a transfer of electron. KMnO4 is a strong oxidizing agent, and it is purple in color. Because it is oxidizing, it gets reduced during the redox reaction. And this is characterized by a color change. The color changes from purple to faint pink. Titration does not require an indicator. And this is because of the presence of KMnO4. KMnO4 is purple in color, and the redox process involves a color change from purple to faint pink. So we don't need an indicator, it is self-indicating. Four, in this particular titration, we are titrating KMnO4 against a standard solution of ammonium iron 2 sulfate. 5, the redox reaction involves two half reaction. One is oxidation, the other is reduction. The oxidation part is we having iron 2 plus increasing toward iron 3 plus, while the reduction part involves MnO4 minus, which is the permanganate ion, transforming towards a manganese 2 oxide. So I need you to focus your attention on what is happening here. There is an increase in oxidation number from +2 to +3 for iron. That makes it oxidation. Oxidation is the increase in oxidation number. And in the permanganate ion, the oxidation number of manganese is +7. How do you know that? You can simply call it X. Oxygen has a -2. So we have 4 into -2. Then you can equate these to -1, being a negative one on top of the manganese ion. So when you isolate X, you end up having -1 plus 8, and that gives you +7, which is emphasizing that manganese has +7 as its oxidation number in manganese ion. Then this here we have a plus what? A +2. So this is a reduction because we have something falling from +7 to +2. Then 6. Understanding the rules for balancing redox reaction is a plus here. You probably might escape it in this exam, but if you know how to balance redox reaction, it's a plus. So I have the rules summarized. Rules for balancing redox reaction. The first approach is to always split the redox reaction into two. One is going to be the oxidation, the other being what? The reduction. Next is to balance every other atoms except hydrogen and oxygen. Next, balance oxygen by adding the required number of moles of hydrogen ion to the side that is deficient of oxygen. Next is to balance hydrogen, and you do this by utilizing hydrogen ion H+. Okay, I think I made a mistake just now. Let me rephrase that. Balancing oxygen is usually by adding the required number of moles of water molecule to the side that is deficient of oxygen. And that balancing hydrogen is achieved by adding the required number of moles of hydrogen ion to the side that is deficient of hydrogen. After you've done balancing of atom, of oxygen, of hydrogen, the next thing is to balance charges. And how do you do this? You utilize electrons. You add the required number of moles of electron to the side that is more electropositive. Once you've done that, you try as much as possible to equalize electrons. Equalize electrons by simultaneous equation. You know, the things you do in simultaneous equation where you do a kind of cross multiplication helps you balance electron, and after that, what do? You combine the two equations together. This particular video won't be able to solve more questions on redox reaction because that's on the scope of this video. But we'll just focus on the one involving manganese, permanganate ion, and what? Iron 2 ion. So let's look at this question together. Here we have an instruction. It says, answer all questions, structure your report clearly, including all tables, observations, and what calculations. We have a provision, solution A and solution B. If you watch closely, solution A is a solution containing 3.92 grams of ammonium iron 2 sulfate dissolved in 100 cm cube of solution. You need to ask yourself what you need to do with this information. What can you see? You can see a mass of 3.92 grams. Mass 3.92 grams. And volume of what? 100 cm cube. Okay, so when you have mass and you have volume, you can easily get what they call mass concentration. Mass concentration is equals to mass over volume. But here, your volume has to be in dm cube. So what do? You divide by what? By 1000. So this is going to be what? 100 over what? 1000, giving you what? 0.1 dm cube. So So this is going to be what? 3.92 gram divided by what? 0.1 dmq. That's if you need the mass concentration. We are going to come back to this later. Solution B is a solution of potassium permanganate, KMnO4, of unknown solution. You know, when you can tell that this is not a standard solution, it is unknown. So basically, the aim of the experiment is to try to find the unknown what concentration. And I said earlier in this video that some question can intentionally give you the concentration and probably label this KMnO4 as maybe no, let's use something like X for the K, then MO4. What am I writing? MnO4. So which means the aim of the experiment here might now be to try to identify what X is by trying to find the maybe molar mass. You know, that helps you to tell maybe, oh, this is what potassium. But in that case, the question would have to supply you the concentration of what? KMnO4. But for now, don't let us take it deeper beyond this. Procedure. We have a procedure involving 7 steps here. They say a pipette 25.0 centimeter cube. So it's a pipette 25.0 cm cube of solution A into a clean conical flask. You have what? A conical flask, right? Let me redraw that. So you have a conical flask, and you want to pipette what? 25 cm cube of solution A into the conical flask. And they said add 10 cm cube of diluted dilute H2SO4 to this conical flask. The job of this is just the medium is serving as the acidic medium. Normally, when you balance redox reaction, you would be able to see that by default, we first attain the acidic medium. So the job of this H2SO4 is just being the medium in this case. Titrate the mixture with solution B from the burette until a permanent faint pink color persists for 30 seconds. So you can see the beauty of this procedure here. You probably do not need to have some expectation before. I mean, you don't really need to know much. The question is even telling you exactly what you need to observe, like seeing a faint pink color in a situation whereby you don't know what you don't know what to expect at the beginning. Repeat the titration procedure to obtain at least 3 concordant titer values. What do they mean by concordant titer value? In advanced chemistry, most time, our titer value should be within plus or minus 0.1 difference cm3. Now, look at this. If I have, let's say, the first titer value to be something like a 12.8 cm3, and I have another to be what? Let's say 12.9 cm3, and I have another one to be 12.8 cm3. These 3 values are really concordant with themselves, meaning I can use the 3 values and sum them together to get the average. But say we have something like maybe among them I have like 13.10 cm3. 12.8 is still concordant with what? 12.9, but no longer concordant with what? 13.0. And 12.9 itself is concordant with what? 13.0. So in this case, I have to pick just any two concordant value here, like 12.8 versus 12.9, or 12.9 versus what 13.0 by neglecting what 12.8. So I'll just add the 2 and divide by 2 in this case. Okay. So for the sake of JUPEB, use plus or minus 0.1. In some chemistry practical, you still see some plus or minus 0.2. But for the sake of JUPEB, focus on plus or minus 0.1 difference. Tabulate your burette readings. You have the initial, final, and the volume of acid used. After this, I will show you a tabular form where we have what? A volume. Calculate the average volume of solution B. Now, so according to this question, the way it is structured, solution B, which is the potassium permanganate, is what will eventually be inside the burette. You get? I will show you a visuals to help you visualize it. Then lastly, it says write a balanced ionic equation for the redox reaction between Fe2 plus and MnO4. Okay. We have a C part of the problem, which says we should calculate the following, like using the experimental data and the information provided, calculate the concentration of solution A in mole per dm³, the number of moles of Fe2 plus present in 25 cm³ of the pipetted what volume of solution A, the number of moles of KMnO4 consumed during a titration based on your average titer volume, and 4, the molar concentration of solution B in mole per dm³. Then they also provided you what? The atomic masses of the atoms or the element present. This is a visual. I decided to put this particular visual so that you can have a colored picture of what is happening here. I have a burette. Inside the burette, you have KMnO4. And the color is purple. Then here we have a conical flask. Inside the conical flask, you have the ammonium ion 2 sulfate. Let me just call that what? Okay, let's write it fully. Ammonium sulfate dot iron 2 sulfate dot 6H2O is hydrated. Then on the right hand side, you still have almost the same thing. But what's the difference here? In the right hand side picture, notice the color of the solution within the conical flask. It is faint pink. You can see that the color is faint pink. So which means what you have on the right hand side is basically the finer, get, is the finer after the titration. Then on the left hand side, what you have is the beginning. Now here we have volumes. This titration has been carried out already, and theoretically we expect to have a 12.5 titer value. So this particular table is based on theoretical what? Calculation of the titer value. So, but what do you have as a candidate in the lab for your exam? This looks too perfect, so you may have to tweak it, and that is exactly why I have what? Another table provided. Here, you ignore the rough and focus on the what? On the first titration, second, and the third titration. So what do we have? 12.5 plus 12.5 plus 12.5 divided by what? By 3. I could use the 3 because all of them are concordant to themselves. So the final result here still remains at 12.50 watts cm cube. Let's call this 0. It's important you have it in 2 decimal places, and do not forget to put your units for the burette reading. If you like, you can put the cm cube here too for visibility to whoever is going to mark your script. So let's make use of this. Now, what did I do here? The first thing was to have a rough titration. The burette was filled to the brim, like you having something like this. The burette was filled to a 0.0 centimeter mark. Okay, this is like a 50 watt, a 50 centimeter cube burette. Okay, it was filled to the what 0.0 centimeter mark. So what did he do after? What do? We titrated. Okay, so after getting to the neutralization point, we have 12.8, meaning the final volume is now at 12.80. Mind you, this is the what? This is the rough value, the rough titration. So then you carry out the first titration. But before carrying out the first titration, I intentionally refill. You realize that I'm still starting from 0. I refilled back towards 0. And on having the first titration, this was the final volume, which is 12.50. The difference in the volume is going to be what? 12.5. You realize that in the second titration, I did not bother to refill. What did I do? Where this one ended, the final here automatically became the initial here. Then we did the second word titration and still got to 12.50. And here also, we did the same thing, we got 12.60. Now, please, this is where your smartness needs to come in. As a smart student, you possibly have no business. I might be, this may not be nice coming from me as a teacher, but you need to be smart as a student in the lab, in an examination lab. If probably an examination is not involved, time is not a factor here, then you can do everything you need to do in the proper way. But because time is a major factor here, you have to manipulate, like you need to be that smart. So what do? You can just carry out the first iteration and just what? After the rough, carry out the first iteration, get your volume of B used, then manipulate the rest. For the sake of your exam, no matter how much they want to twist your paper tomorrow, twist your examination for this particular concentrations given, the titer value is going to be approximately 12.50. So you can play around that. So you have an expectation already, right? So here, having 12.50, 12.50, 12.60, I can't neglect any because all the values are concordant with themselves. They are within 0.1 difference, 0.1 CMP difference. So in that case, I use the 3, added them together, divided by 3. Approximately, we have 12.53 cm3. So this is the volume of B, and that part of the problem has been solved. Now we'll move on. So we've dealt with 1, 2, 3, 4, 5, then 6. So now it's time to find out 7, which is write a balanced ionic equation for the redox reaction between Fe2 plus and MnO4. Okay. So this is Mn4 minus and Fe2 plus. This is the oxidizing agent here. it will get reduced to what? Mn2 plus, while the iron 2 plus will get oxidized to what? Fe3 plus. Rule 1, you split it into two half equations. So one is the oxidation, Fe2 plus, to what? Fe3 plus. So you call that the oxidation. Then Mn4 minus to Mn2 plus. So this is what? Reduction. So while trying to balance this, I would advise you to space it. Let's do some spacing. Let's write the first one. Fe2 plus to, I gave a little space, and we have what? Fe3 plus. So do not forget, first rule, balance every other atom. Every other atom here is balanced. Like we just have iron here, and we just have 1 mole versus 1 mole is balanced. There is no oxygen, there is no hydrogen, so we don't need to bother about those. So what do we need to do now? We need to balance charge. What's the total charge on the left hand? +2. On the right hand, +3. So because of that, we have a side that is more electropositive, which is the right hand side. I need to reduce this to the level of this. So how many electrons? Electrons are negative. When you want to reduce something, you add negative to the equation. Okay, you add negative to it to make that thing less what? Positive. So want to make the right hand side less positive. How many electrons do you need to do that? It's going to be 1 electron. So basically you are done with what? The first half equation. Then let's look at the next half equation, MnO4 minus MnO4 minus. Then you put a little space so that, okay, then we have Mn2 plus. Balance every other atom except oxygen and hydrogen. Every other atom that we have is just manganese. Is balanced. We have 1 mole of manganese in both sides. Then balance oxygen. How do you balance oxygen? You do that by adding water molecule to the side that is deficient of oxygen. My right hand side does not have enough oxygen to balance the one on the left hand. Oxygen on the left hand 4, on the right hand none. So add 4 water molecule to the right hand side. Oxygen is balanced, then that introduce hydrogen into the system. We need to find a way to balance that. On the left hand side, no hydrogen. On the right hand side, 8 atoms of hydrogen. So it's unbalanced. You balance hydrogen by adding hydrogen ion. So how many hydrogen ion do I need to add to the left hand side? Now it's going to be 8. So this will help us balance what? Hydrogen. Now that hydrogen, oxygen, atoms are balanced, we need to focus on charges. So what's the total charge here? On this, I have -1. On this, I have 8 times +1, which is +8. When you cumulate that together, -1 and +8, that's +7 in total. Okay. Then I have +7 on the left hand in total, right? Let me rewrite it the way it was before so that you can get the gist properly. And here we have a +2, and here we have 0. When you add those two together, that gives you a +2. So now we are having a +7 competing with a +2. So there is a difference of 5 between +7 and what? +2. So that gives you the idea of the number of electrons you need to add to the system to balance the charge. And you add the electron to the side that is more electropositive. So we're adding 5 electrons towards the left-hand side. So you have done a balancing of atoms and charges. Let's equalize electrons. We have 1 electron here, and you have 5 electrons here. So For us to combine these two equations, we have to find a way to balance that force. You remember in elimination method in simultaneous equation, you tend to do a kind of cross multiplication with the number of moles of what you want to eliminate. We want to eliminate electrons here. We have 1 mole of electron on the first. You multiply the second by 1. We have 5 mole of electron on the second. You multiply the second by 5. So this then enables you to make this faster. I will just do a copy and paste on the next page. Okay, so you have this. So if you multiply that by 5, you end up having 5 here, 5 here, and 5 beside what? The electrons. You get that? And when you multiply the, I had 1 here. When you multiply the second one by 1, it doesn't change anything. So let's take it away. So now we can combine the first two. We can combine everything on the left versus everything on the right. So let's do the combination. So when you do that, the electron is going to cancel out. So you then have 5 what? Fe plus, Fe2 plus what? MnO4 minus plus 8H plus what? 5 what? Electron. So the electron is eventually, the 5 electrons is eventually going to cancel out. So don't let us bother. So giving us, we have 5 what? Fe3 plus what? Mn2 plus, then plus what? 4H2O. Now, if you watch closely, everything is balanced. Looking at iron, 5 versus 5 on the left versus right. Looking at manganese, 1 versus 1 for left versus right. Looking at oxygen, we have 4 versus 4 for left versus right. Looking at hydrogen, we have 8 versus 4 times 2, which is also 8 for left versus right. Then looking at overall charges, we have 5 times plus 2 plus 10. Here we have minus 1. And here we have 8 times plus 1 plus 8. Add everything together. What do you have? You're going to have plus 17. On the right, we have 5 times plus 3 plus 15. Here we have plus 2. Here we have 0. When you add everything together, we have plus 17. This is an indication that you have it what? Balanced. You get that? Okay. So what you need here is just the final what? Equation. You get the final equation, which is giving us the final redox reaction. The final redox equation, or you call it the overall redox equation. This is what they want to see. And this is in acidic medium. Why? Because we ended up retaining hydrogen ion as an ion there. Okay. Let's focus on the ratios. The number of moles of iron versus the number of mole of what? Permanganate. So this is 5:1. Please take note of that. 5:1. We're going to make use of that. All right. Moving on to another calculation part. This says, using the experimental data and the information provided, calculate the following. Number 1, we need the concentration of what? Of solution A in what? Mole per dm³. Then you need to go back and check the information provided. Now let's go back to the information provided. Recall, we have the mass given as 3.9, or let me just say, I've explained this earlier, the mass concentration here is mass in gram over what? Volume in dm³. So this is going to be the mass of the solute supplied is 3.92 gram over the volume in dm cube. They gave you 100 cm cube. Convert to dm cube by dividing by what? 1000. So that's 0.1 dm cube. So the mass concentration is then going to be the 0 shifted by 1. So this gives you what? Or just multiply up and down by 10. So this gives you what? 39 point what? 0.2 gram per dm cube. This is called mass concentration, or you say concentration in gram per dm cube. But is that what the question needs from you? No. The question wants concentration in mole per dm cube. So you need to know that concentration in mole per dm cube, which is also called the molar concentration, is usually given as concentration in gram per dm cube, which is called the mass concentration, over molar mass. So just get the molar mass and you're good to go. Molar mass of what? Of this salt. What's the salt labeled A? The salt labeled A is what? This guy. It looks gigantic, so you just have to go through the stress of looking for the molar mass. You have the information supplied, so let's quickly get the molar mass from here. We have NH4. Let me just do that on the next page. I have NH4 into what? 2 SO4 dot what? FeSO4 dot, we have 6H2. Please, the dot you are seeing here is not going to be multiplication. You'll just be adding them up. You know, you find the molar mass of NH4, 2 SO4, and FeSO4, then that's of water, then you're good to go. So nitrogen is nitrogen is 14. This is nothing, you don't have to cram it, it's given to you. See them here. Okay. So nitrogen is 14. Hydrogen is 1. So here I have 14 plus what? Plus 4 times 1, which is 4. Then times 2. Then plus sulfur is 32. You have it here. See. And iron is 56. Oxygen is what? 16. Sorry, that's an addition. 16 times 4 is 64. Then plus iron is 56. Sulfur is 32. Oxygen is 16. 16 times 4, 64. Then plus 6 into the bracket of H2O. H2O as O is 18. Add that up. So let's try and add that up. Where's my calculator? 14 plus 4, 18. 18 times 2, you have 36. So you have 36 plus 64 plus 32. So that gives you 132 here. Then we can add it together with plus 56. Let's just add it straight. Plus 32 plus 64. Then plus 6 times 18. So that gives us a total of 392 gram per mole. Gram per mole. Okay. So that is having a kind of rhyme with the information supplied here. They gave 39.2. So what do we need? We need the molar concentration. So we can say that the molar concentration of A, let me put it here, Ca, is going to be the mass concentration, which we have as 39.2 gram per watt per dm cube, divided by the molar mass, which is what? 392 gram per mole. Now take note of the unit. The gram cancels out. So you end up having, this is going to be 0.1 mole per dm cube. So that's the information you have for the what? Molar mass. You get that? Okay. So you can probably put it in 3 decimal places, not necessary, but since it's a calculated value, let's put it in 3 decimal places. So the next question is telling us to find the number of moles of iron 2 plus present in 25 cm cube pipetted volume of what solution A. We need the number of moles of iron 2 plus. Okay, that is present in 25 cm cube of solution A. What's the concentration of solution A that we calculated? 0.1. So C of A itself is 0.1 mole per dm cube. Volume of A that was supplied in this particular question, I mean here right now, is 25 cm cube. That was the volume of the pipette, remember, right? So 25 cm cube, convert that to dm cube by dividing by 1000. So we need the number of moles of A. Number of moles of A is going to be CV, CAVA. So this is going to be 0.1 times 25 over what? 1000. So what would that be? That's like saying we have 2.5 times 10 raised to the power minus 4. Is that correct? Yes. 2.5 times 10 raised to the power minus 4 mole. Or you can probably write it out, a choice, 0.00025 mole. Please, that's your choice. The question asks for the number of mole of iron 2 plus present. If you look at the salt A itself, you know it is NH4 into 2 SO4 dot Fe SO4 dot what? 6H2O. Okay. This, you can see that here we just have one atom of iron 2 plus here. Because we have one of iron 2 plus there, you get? So it's just going to be in alignment with what we have here. Okay. So in that case, the number, I think we have something like Fe2. You have to, for you to know the number of moles of iron there, you have to multiply by 2. All right, now our number of mole of Fe2 plus that the question needs is going to be the same value as our Na, and that is going to be 0.00025 what mole. Next question. This says we should find, that's number 3, we should find the number of moles of what KMnO4 consumed during the titration based on your what average value, average titer value. So number 3, what's our average titer value? We got that as what? I think 12.53. This is it here. 12.53 was our average titer value, CMQ. So we have this to be equals to what? 12.53 CMQ. Now, what does the question need? Number of moles, right? It says number of moles of what? KMnO4 consumed during the what? Titration based on your what? Average titer value. Okay. So we need number of moles. Is it? Number of moles of B. So, you know, if we have the concentration of what? B, we can easily calculate what? This. You know, this is something we can easily calculate. But we really do not, we just need, we can go back to the equation. Let's Let me see if I still have the equation on the clipboard. Yeah, I have it here. Now, in the equation, this is the KMNO4, which is labeled B. This is the Fe2 plus, which is labeled A. The ratio between them is what? 5:1. Meaning for every one of MnO4 minus, we have 5 of what? Fe2 plus. You get that? So since we know the number of moles of this guy, are you there? We know the number of moles of this guy. We can easily use it to get what? The number of moles of what? The corresponding number of moles of this. I'm sure you understand that. So we know that 5 mole of Fe2 plus gives what? 1 mole of what? MnO4 minus. Therefore, the number of moles that we calculated for Fe was 0. What? Or let me just use 2.4 exponential minus 4. 2.5, sorry, times 10 raised to minus 4 mole of Fe2 plus is going to give us, let's call it X. So our X now, let me just call it NB. So from there, our NB is going to be 1 times what? 2.5 times 10 raised to minus 4 over 5. So dividing that by 5, what do you have? You have 0.00025 divided by 5. So that gives you 5 times what? 10 raised to the power of what? Minus 5. Minus 5 mole. So that's the answer to that problem. Another way is you go ahead and calculate CB. After getting CB, you can use what? N equals to what? CV to get your answer. It's your choice. So the last question, asking us to find the what? The concentration of what? Solution B. Concentration of solution B. Can just use the formula Na over Nb equals to what? CA/VA over what? CB/VB. So we need the concentration of what? Solution. Where is it? Of solution B. So you need CB. So Na, based on the equation we have here, see the equation. Or let me just compare and paste it here. Based on the equation you have here, do not forget that what? Your B is the MnO4. This is your A. So basically you have 5 over what? 1 by the number of moles you have here. Okay. Equals to Ca. What do you have as Ca? We calculated Ca earlier at 0.1 mole per dm cube. So 0.1 mole per dm cube times Va. That's the what? Volume of what? A. And what was the volume of A? Let me go backward so that you can see. That's the volume of the what? Pipette. Volume of A was volume of pipette, which was 25. So, or you can go back to the question. Where is it? Now, oh, okay, yeah. Volume of A was volume of pipette. This was 25. This is it here. Or just go back to the volume of pipette. Now, the reason why you have a little flip in my head is because, you know, this particular problem intentionally made B the acid and A the base. Usually, we have Na versus Nb. The A will be the acid and B will be the base. So there is no problem though. So here we have 25 watt CMQ. Then over CB that we are looking for. then times volume of B. Remember, we have it as 12.153 cm cube. I didn't bother to use the dm cube because cm cube will cancel out here. So from there, what do you have? CB is going to be equals to, make it the subject as 0.1 times 25 divided by 5 times what? 12.53. So you have 0.1 times 25 divided by 5 divided by 12.53. So this gives you 0. What? 0.399 approximately. This is 0. What? 0.04 mole per dm cube. So that's the volume of B that we are looking for. I'm sorry, the concentration of B in mole per dm cube. Another way you could have solved that is the fact that you know that we have calculated number of moles of B here. Can just use N equals to CV and still get your results there. All right. This marks the end of this class. Thank you for listening, and see you in the next class. Do not forget to like and subscribe to the channel. Thank you.